All right, well, what's on the bench? This was sent into the channel. I've actually had this for several months now. They've been working on the product, and they're going to have a kind of a Kickstarter thing, and they wanted to delay my videos later and get some feedback from me before they release the product. So anyway, this is from Euler Precision. It is an eSAP-30A, and like I said, this is the engineering sample. Yours may look a bit different when you get it. I know they're going to change things a little bit, but what comes in the case? All right. First of all, what is it? It is an active probe for an oscilloscope, right? It's an active probe. It's a 3 gigahertz active probe. It's not a differential probe, it's a single-ended probe. Let's just pull the probe out first. This is the probe. Now, I've done a bunch of videos on active probes before, and one of the headaches of active probes is that you have to get power to it, right? So I've showed the active probe that I now use a lot on the channel, this one, and it relies on you having a correct oscilloscope and a correct interface on the oscilloscope probes to supply power to this thing, right? And other ones sometimes use an external power supply. This one has a battery. So it has one of those big lithiums, the 18, I never remember the numbers, those big lithium batteries. We'll see it later. It has a big lithium battery in it. So that's an advantage. It has its own built-in power supply. Okay? And this is the on-off button for the power supply. So the way you would use this thing is there is an input port and then there's an output port. The output port is 50 ohms and 50 ohm cable, and you put that into your oscilloscope at 50 ohms, and that's the way you use the active probe. Now, let's see, one of the negatives right from the get-go is you cannot hand hold this. Many times in the literature, it says not to be held by hand. And I think that's because you couple, it's not shielded well, I guess, and you couple stuff into it and it doesn't work quite right. So they want you to use this hands off. And because of that, they give you this little, let's see, how do you put this thing together? It's a little tripod. So you can stick the tripod, and then it can hold the thing on the bench, right? So anyway, that's kind of a little gimmicky thing. So it's to be used in circuit. All right. Okay, so that's the unit. It comes with a charger. I'm told that the charger will be black in the future. And this one is this is from Germany, I believe, Switzerland. Yeah, made in Switzerland, and so it has a Swiss connector on it. It comes with an adapter as well for your country. It comes with a charging cable. These cables are mine; they were not included. And then it comes with the probes. Okay, and so. Let's see here. I dropped. So they are gonna make the case a little, make it fit better. Okay, it does come with a few things for the probe. So let's just get that kind of situated. So here is so these connectors are called MCXX, and they snap onto the front of the instrument. Okay. And then that's the way you connect this, is through these. Now, I'm not a big fan of these connectors, and I'm a little curious of why they chose it. They do claim that this connector does add a few picofarads to the loading. I don't know why they didn't go to SMA. I would think SMA would load it even less, but they must have had a reason not to go with SMA. But that would have been my choice. The specifications for this thing is the input it's a 10-to-1 probe, and it's 1 megohm less than 3 picofarads. And they say the connector itself adds a couple picofarads. So that's their limitations. Okay, so it comes with these two cables. One is just MCXX to MCXX. This one is MCXX2. Those little snap-on connectors that like fail immediately. Anyway, they included one of those, and then they included a little kit here with a bunch of things that are the more useful things. And so let's take a look at those up close. Okay, let me separate these because a bunch of these things are mine and they are not included. All right, so these are mine. These are mine. So these were all included here. Okay, they included these little flex circuits. Okay, and they have a connector on it, so you can connect this directly, and then now you have this little two wires that come out. Now, I found these things very troublesome. I could not get solder to stick to them at all on the ends. They're very, very, very difficult to solder. So I think they need to redo the thinking of this particular product. They also include a 50 ohm resistor at the end, which in some ways negates certain things and other ways helps certain things. It does reduce some ground bouncing or signal bouncing and stuff at the end by having a little bit of resistance out there. And it is going into a 1 megohm resistance, but I did measure the impedance of this trace here, and it's about 120 ohms. This just doesn't seem to be quite right to me, unfortunately. They give you a couple versions. This one is really, really interesting. I don't know exactly why they did it this way, but it kind of has a serpentine crisscross with a whole bunch of vias. I'm not sure what they tried to accomplish on that one. This one doesn't have a connector on it, and this one is a different one where they said, well, let's leave one end really long for the ground, and then this is the signal, and so you can kind of get it over to where you need to go. So think about this. You're always thinking about soldering this to the circuit you're going to be measuring. There's no such thing as probing the circuit and moving on. You have to have something you want to measure directly and solder this into the circuit, okay? It did come with this little board, which I found more useful, actually. So it is a female connector. So you use their male connector, and then it comes out to a board, and then you actually can solder things to it. So I put some 30 gauge wires on it, and I soldered this into the circuit, and I got this to work. I just couldn't get these to work. Comes with an adapter, and then it comes with this. I don't know if they're going to include this long term or not, but they said if you wanted to remove the connector on the product and replace it with just a header, you might be able to get rid of a few picofarads, but then you're at the mercy of making all of your own probes and stuff. So this seemed kind of like a non-starter as well. All right, so let's see here. I think the next thing to do is let's discuss the actual device itself, how it's designed and what it's trying to accomplish. All right, if you've looked at active probes before, you might have seen a circuit like this. This is like a very, very simplistic active probe where it's just an FET source follower. It's just a simple thing, okay? But obviously, this is fairly limiting in what it can do. So if you take a look at the actual circuit that's inside this probe, it's a very long PC board, right? But only that much the PC board really does anything. All that other stuff in the back is just battery and battery management and charging and DC to DC converters and all this. It's all power supply stuff. So we really don't care about any of that. This is the only thing that we care about, and it's only really two ICs, this one and this one. All right, and I put some markings on here. I started reverse engineering it, and I wanted to see if it matched something that I had seen before. And so if you look at the part number of the big chip, you will find that it is a Texas Instrument Buff 802. And the Buff 802 is a 2.3 nanovolt per root hertz high impedance buffer amplifier, good for oscilloscope front ends. Yes, sir. High impedance slew rate, blah, 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 and active probes. There you go, active probes. So this is a chip that's meant just to do this. And if you look in the back, all right, let's look at this schematic here. This is the oscilloscope front end amplifier design. And so this is the buffer. This is the Buff 002, and uses an OP140 as a reference ground. Basically, it's a buffer for the reference ground. And you have a resistor divider here, 800K and 200K, and then on the output you also have an 800K. Well, it's the same ratio, okay? And this looks at the two of them and sets that. Now, OP140, if you take a look at this is an OP140. So it's exactly the two chips that you see in this application. And if you reverse engineer this, I didn't reverse engineer it all the way, but basically it's the Buff 02 and the OPT 140, and there's an 800 and 200K dividers here, and there's a divider here, and those two dividers then get compared by the 140, and then it feeds back in. So it's very, very, very similar. It's not the same, but it's very, very similar. There's an extra little 1 meg resistor shoved in there. They probably needed to add a little bit of maybe positive feedback to increase its working ability. See, there's a little bit of feedback here. This 10 megohm resistor thing, they did it a little bit differently. And you can see here, this one has a potentiometer here to adjust the DC bias and everything, this thing, so that you have this divider and this divider matched together. They did a little bit different. They adjust the front and fix the back. It's the same thing. Anyway, so it's very similar to this, but not quite. So anyway, there you go. It is a Buff 002 and a OP 140. And so the data comes in here. It goes through a 51 ohm resistor and then a couple of capacitors in series. Kind of interesting, they use two capacitors. So you go through two capacitors, then it goes into another 51 ohms into the chip. So, but then the input gets divided down and it gets sampled off of that. And then the output is buffered by a 50 ohm resistor to the output connector, okay? And then it's also, part of that is sneaked down here over to the DC offset compensation thing. All right, and then there's a bunch of capacitors. These capacitors and these resistors and stuff just buffer VCC, and yeah, a couple little roll-offs and other voltage dividers and stuff in there. But anyway, it's not too complicated. I'll let you take it apart if you really want to do that someday. But it is based off of a TI part that was built to do just this. So there you go. The Buff 802 is good to 3.1 gigahertz, 50 gigohm input. Very nice. 2.4 picofarads. Okay, so like I said, there's a button here you press and you get a green light. So what we're going to do is we're going to measure a few things. We're going to measure the input impedance of the device. We're going to measure the loading of the device. We're going to measure the transient response of the device, the rise time of the device. All right. So the unit comes with a measurement report for the product. It says serial number. I don't see a serial number on the. Oh yeah, here's a barcode with a serial number. Yeah, the serial numbers match. So this is the measurement from this device. So let's see if we can duplicate these measurements. This one here is an S11 measurement. That's simpler, so let's do that one first. Now it says the test conditions here are 5 kilohertz to 3000 megahertz. Input power of -20. Okay, that's interesting. Let's see, measurement. Okay, so measurement consists of a coax cable with a 9 dB attenuator positioned close to the dot. Okay. So they're not measuring it directly, they're measuring it through a... Isn't that going to screw up your S11 measurement? All you're going to be measuring is the S11 of the... I think maybe this is in error. This doesn't make any sense to me. Let's measure it without that 9 dB attenuator. They have another measurement where they use the 9 dB attenuator. I think that might be correct, but this must be incorrect. I don't know why you could do that unless you calibrated through. No, that doesn't make any sense either. You would ruin your VNA measurement by doing that. So anyway, let's assume that that's an error in their piece of paper. But let's see if we can't measure the S11. So we're going to need an adapter. I bought an adapter. I didn't have one. So this is a MMXC to be in SMA to MMXC. And so we'll put that on the front. And I've already calibrated my VNA here at this cal location at the end of the cable. So we don't need to do a port extension or anything. We should be good to go. So let's plug that on. Let's go ahead and turn the device on. All right. Oops. Let's see here. Let's make sure these are tight. There we go. And I'll plug it onto the device. And all right, let's go over here. It's about right there. Let's get a Smith chart. And yeah, that looks something like theirs. Let's see here. 50 ohm system, there we go. Okay, so it's following, theirs kind of follows the 50.1, 0.35, yeah, theirs kind of follows this 25. Do you see what I'm saying here? The real values are 100 ohms, 50 ohms, 25 ohms, and then the real part follows these curves, and so you come along here. Theirs kind of follows this 25 curve. Mine's a little bit wider, but theirs does the same thing. Oh yeah, because they go to 3 gigahertz. So M2, 1 gigahertz. Oh yeah. Yeah, we're getting about the same value. So I think that their measurement report is in error. I'm going to point that out to them. So that is S11. And they're claiming at 1 gigahertz, they're getting 2 picofarads. So let's get a marker here at 1 gigahertz. We are getting 2.5 picofarads. They're measuring 2 picofarads. Yeah, close enough. All right, so I can't go to 3 gigahertz on my machine there, but I believe they're So my machine can only go up to basically this location here, the M2 mark. This is the 25 ohm line here. And yeah, we're getting about the same. And then there's curves in because they go to 3 gigahertz. Okay, fine. And then the other measurement, which is a little stranger, is the S21 measurement. Now, this one I do believe about their attenuator. They're going to run an attenuator close to the dot, and then adapters on both ports, and then they're going to hook it up into an S21. Okay, so let's do that. So what they did was they put in a 9 dB pad. My camera's off. You're off camera here. Okay, so we're going to remove the connector here. We're going to get a, let's see here. I don't have a 9 dB, but I have a 10 dB. We'll put in a 10 dB attenuator at the end of the first cable. So now we're going to have 10 dB lower here, okay? And then we'll go ahead and put our adapter on here. And we'll put an adapter over here. I don't have another one of those adapters, but I have a little short cable, which should be okay. So let's do this. We're not looking at phase information. We're just looking at oh, it's kind of hard to get a wrench on that. That's close enough. That's close enough. All right. So let's go change our system here to transmission. And let's see, we need to calibrate this system. So I have a male MMXC, and we'll put that right here. And there you go, it's already calibrated. So nice straight line, so no need to cal it again. All right, so that's looking good. All right, so we're gonna put in, let's see here, it says measurement is done at -30. Okay, and our power is already set to -10, so let's put it at -20. Okay, so -20 is going to be going in, and then through the pad it'll be -30, and that'll go into the device. And then we need an adapter here on the BNC. Ah, no, we don't. I'm sorry. We do not need it. We're not going to use this cable. We're going to use the port directly. So we'll unplug there, and we'll plug me in. Okay, there. That's how it's done. That's why they needed the. That's why they needed the adapter. Okay, plug that in. All right. And this fell out. All right. This barely reaches in because of the. I could use their little tripod, I suppose. There we go. Oh, there we go. All right, now they claim -14 dB and pretty flat. I'm measuring from 300 kilohertz to 1.3 gigahertz. All right, let's go ahead and set the scale reference level to -14. And let's set the scale per division at 5. Let's set scale per division at 1. Okay, their scale per division is 0.5, so let's do that. All right, so we've got some wigglies. We can do some averaging, turn some averaging on, make it a little bit quieter. And then their resolution was 1 kilohertz. System bandwidth, I'm running at 3.7 kilohertz. We can go way down and narrow, make it as clean as we can. That's not going to matter. That's not going to matter. It does a little bit, I guess. It does a little bit. All right, we'll just let it sit like that. But anyway, you get the idea. So they claim 14 dB, and at 1 gigahertz, it kind of goes right to 14. So I'm not getting the same measurement that they're getting. And I'm getting a little bit more wiggles than they're getting. So I don't know about the measurement. Let me go ahead and try one thing here. I'm going to move, since they don't have that connector, I'm going to put the long cable on the input side and the short cable on the output side, just to see if that makes any difference at all. I should get another one of these adapters. All right, let's see what we're doing here. Let's turn averaging off. And let's change our system bandwidth back so it's nice and speedy again. It changed it a little bit, but not enough to write home about. Anyway, so we're getting some wigglies that they didn't see on their machine. They have this real smooth plot, and I get a wiggly plot, so I'm not sure what's going on. All right, I'm going to do a test looking at a sine wave with the two different probes, the Agilent probe and the Euler probe. I'm going to be taking the signal, I'm going to be splitting it 4 ways. I've terminated one of the ways. One of the ways is going to go straight into the oscilloscope. And this one's going to go through the Euler. This one's going to go through the Agilent. And the input will be coming from way over there. It is a Agilent, what's part number? 8648B? Anyway, it's good to 2 gigahertz. All right, so let's go here and let's adjust the camera a little bit. There we go. I'll get in a little bit closer. All right, that's pretty good. All right, so the green trace is the Euler, and the blue trace is the Agilent. All right, and we are at 460 megahertz. So I'm gonna lower it down. All right, and I'm gonna go up and up and up and up, and here I'm at 580, 680, 810, 860, 900. So at 900, we're getting a phase shift, and the Agilent reads a little bit low. And then as we go, and we're here at a gigahertz. Okay, so at a gigahertz, it seems as though the Euler is measuring correctly. Now let's kind of look at it across the band, see if it's staying kind of at the same amount. It's going to go up at the low end. So like here, it's kind of peaking right around 350 megahertz. My coupler's not good below. My coupler's going to drop off. But I think, I think they're probably both fine. If I had to put money on it. So like the oscilloscope's only good to a gigahertz, and my active probe, the Agilent, is only good to a gigahertz. So here is a gigahertz, and so it is rounding off. Let's go ahead and go higher. Oh, and that's just disappears. Yeah. So the scope just disappears. If it gets too high for 1100 megahertz, it just gives up the ghost. It says nope, we're not playing that game. So here's 800. Here's 800 megahertz, and they look identical. So that's a pretty cool test. I like that one. All right, I'm going to use my fast oscilloscope here to measure the rise time. The 20-80% rise time seems to be about 116 picoseconds, and the 10 to 90 looks to be about 173 picoseconds. So, best my estimation, it's 2 gigahertz rise time. All right. So my overall impression of the device is. You've got to have a real use case for it. Like I said, you can't hold it by hand. You have to hand solder to the circuit. Yeah, it will monitor certain signals on a PC board. So I think if you're in the process of tracing particular fast signals, maybe even digital signals on a PC board, then maybe this is a good tool for you. For me, it's, I mean, they compare it to this Agilent sensor, and it's just, there's no comparison. The Agilent sensor is so much better for the stuff that I do. This is a little bit faster, so that may be of interest to you. But like I said, I think you really have to want one of these in order for you to justify probably what they're going to be asking for it.